So thank you all for coming. I am James McNellis. I'm an engineer at Microsoft where I work on our time travel debugging toolkit, which I am excited to be here to talk about with you today. So before I begin, I'm just curious, how many people here develop exclusively or primarily for the Windows platform? This is a show of hands. Wow, that is excellent. So for the benefit of the people on YouTube, everybody in the room raised their hand. This is a wonderful audience we've got here. All right, not really, but how many people here spend at least some time developing for Windows or have in the past developed for Windows? So, okay, that's a sizable group of people. So the time travel debugging tools that I'll be discussing today are Windows-specific, but I hope to keep this talk interesting for everyone here, even if you don't develop for the Windows platform. If you do develop for Windows, then the content may be directly useful to you in your work. If you don't develop for Windows, that's okay. Nobody's perfect. Then hopefully you'll still enjoy learning about some new debugging technologies. When I attend conferences, I often like to attend talks that have nothing to do with my day job because it's my opportunity to gain some breadth knowledge. So with that, this talk will consist almost entirely of demos, but I have a few slides to start with to set the stage. So first, what is time travel debugging? So time travel debugging, or TTD as we abbreviate it, is a reverse debugging toolkit. And you can use it to record execution of a program as if you were recording a movie of everything that the program does, every instruction that is executed inside of the program. This recording gets stored into what we call a trace file. After the recording has been created, you can then open the trace file in the debugger and replay it forward and backward. Just like if you have a DVD of a movie, you can fast forward and rewind. With a movie, you might seek through it to find a particular action scene that you want to rewatch. With a trace of a program, you're likely to want to seek through the trace to find where a particular bug happened. In addition to being able to seek forward and backward, though, you can also query the contents of a trace file as if it was sort of a database. And I'll discuss this in detail in a couple of the later examples, but for now, just know that this makes pinpointing a bug far easier. So why time travel debugging? Well, we have some problems that we want to solve. First, debugging is time-consuming, and I'm sure that many people here are familiar with the tedious experience of carefully single-stepping through a program because you don't know exactly where a bug occurs and you don't want to accidentally step over the place where the bug happens. Debugging is hard. Of course, most problems that we debug are trivial little things, and it just takes a few minutes to find it and solve it. But most of the time that we spend debugging is usually not spent on those trivial bugs, right? It's spent on tricky, subtle bugs that we can't reliably repro, or bugs where the problem occurs very far away from where it actually manifests as program misbehavior. Time travel debugging is especially useful for these kinds of bugs, which are otherwise difficult to debug. Debugging is complex. We already have all these specialized tools to help us debug, and we spend a lot of time learning how to use those tools effectively. We don't want our time travel debugging tools to make debugging unnecessarily more complex than it already is. So with TTD, we've worked hard to make the experience as similar as possible to the experience of debugging a live process, just to keep everything familiar. So things like setting breakpoints or single-stepping still work with time travel debugging. When we do have new time travel-specific capabilities, we've worked to make them as intuitive as possible and tried to make them fit in with the rest of the debugger functionality as well as we can. Finally, debugging may require multiple repros, so there's two different sides of this to consider, actually. First, you might have a bug that does not reliably repro, right? It might be a race condition that only occurs occasionally and under specific circumstances that are hard to pin down. Or maybe it's a bug that a customer hits reliably, but you're unable to repro on your own machine or in a test environment. Everyone here is familiar with the joke bug resolution. It works on my machine, but that is not an answer that makes customers happy. But second, even if a bug occurs reliably, and even if you can repro it locally, the repro may be time-consuming to reproduce, right? You may have to spend time getting the program into a particular state or run through a long list of steps to cause the bug to happen. This is problematic with live debugging, where you may have to repro the bug multiple times in order to fully debug it. For example, if you have a crash, the crash may occur due to a problem that occurred long before. You might start debugging the crash by running the program and running through all the steps to get to the point where it crashes, and then you inspect the state of the program. And that state will give you some clues as to, well, where's the next place I should look? And so then you'll go set some breakpoints, and you'll go start over. You'll start back from the beginning and move forward again. And then you repeat this process over and over. Many of us have probably had the experience of binary searching for a bug, right? You stick a breakpoint in the middle somewhere and you say, has the bug, when it gets hit, you say, has the bug happened yet? If it hasn't, then you keep running, set some breakpoints later. If it has, then you set some breakpoints before. So with time travel debugging, you only have to record the bug happening once. Once you have a trace file, you can replay that trace and seek forward and backward in time as necessary to determine the root cause of the issue. And this makes time travel debugging a tremendously powerful tool. So just a few features, a little information about it. Where did these come from? So our TTD tools originated as a Microsoft research project, and they've been used internally at Microsoft for over a decade now. A few years ago, we decided to polish the tools and get them into a state that we could, such that we could release them publicly, because we wanted all of you to be able to use them as well. And we shipped the first preview last September as part of the WinDBG preview. We did that in conjunction with an announcement talk at CPPCon. We don't require you to make any modifications to your programs. You don't have to rebuild your program or link with anything special or make any post-build modifications to it. You can just record programs as they are. All of the examples I'm going to walk through today use programs built directly using the publicly shipping Visual C++ toolkit. I've got nothing up my sleeves. A few features of the actual implementation. So we can record multiple threads in parallel. Some reverse debugging tools will serialize execution of your program, kind of like if it was running on a single core CPU. TTD does not do this. We can record basically an arbitrary number of threads executing in parallel. And we find this to be very important for debugging large and complex software systems, of which Microsoft has many. We can record programs that use shared memory and async I/O, so some other tools have some difficulties with one or both of those. And then, like I mentioned, we have the ability to query data from a trace. Time travel debugging, it's a three-step process. So first, you record execution of your program using the debugger. While you're recording, you do whatever in your program that you need to repro the bug. Then you can kill your program, or it'll crash, whatever. Then the debugger will open the trace file. The trace file is actually stored in a format that's very convenient for us to write to. Basically, we want it to be as efficient as possible for us to write to so that we have, we minimize the overhead we impose on your program. But this format is not particularly convenient for us to replay inside of the debugger. So the first time you open the trace in the debugger will automatically index the trace, and it'll aggregate a bunch of information about what's in the trace to help the debugger do its thing. Then finally, once the debugger has done that, you can debug the trace. As I said before, most things work similarly to how debugging of a live process works, and we'll get to all of that in a minute. Finally, you can find the time travel debugging documentation and all the information of how to get it and such at this aka.ms/TTD. We have a great documentation team, and they put together some nice tutorials and usage tips. So everything that I'm going to describe today is also detailed in there, with walkthroughs and things like that. So, all right, some things are easier to show than to talk about, and it ends up being a lot more interesting that way as well. So for the rest of this talk, I'll be walking through a few examples of using TTD, to show you the features, show you things that you can do with it. So first things first, how do you record a program and then debug the trace? Well, actually, before we get to that, how do you get time travel debugging? So first, you have to be running Windows 10. If you're running Windows 10, you can just open up the Microsoft Store app, search for WinDBG, and then there'll be this nice install button. I already have it installed, so it says launch. But you can install it. It is free. However, if you would like to pay a licensing fee, I'm happy to accept cash after the talk. The other thing I wanted to point out here is it's actually rated E for everyone. We are confident that these tools will make your debugging so easy that there will be no need for any strong language that would require a higher rating than that. Okay. Once you have it installed, you can run it, and in order to debug or in order to record execution of a program, you have to run it as an administrator. So I'm just going to right-click and go to More and Run as Administrator. Great, so here we have WinDBG. If you've used WinDBG in the past, then this may not look particularly familiar if you haven't used the new preview from the store. We have this, in the preview, we have basically this whole new UI that we've been working on to try and make it much easier to use, much more user-friendly. So we have WinDBG open with admin privileges. Let's record our first program. So from the File menu, I'm going to choose this Launch Executable Advanced, and you can see here in the little information, it supports time travel debugging. and I would browse to find my program, which it's already got populated because I just rehearsed this before my talk. And I'm going to check this checkbox that says record process with time travel debugging. And I get to choose where it's going to store the trace file, but this is fine, the default. So when I click OK, the debugger is going to run the program and record everything it does. The debugger will not be attached to the program, so I can't break into it or set breakpoints or things like that. Basically, it's just going to run the program and record what it does. So I'll click OK. We can see this program is not very exciting. It just prints out some strings, and then it's going to exit. And then, as I indicated before, the debugger is automatically going to go take the trace file. It's going to open it up. One of the first things that it will do, that I'll highlight here, is it's going to run this index command to create the index. And then after that, it positions itself at the beginning of the trace, so where we started recording the program, and now we can debug the program. And we can see that we're near the beginning because this LDR initialize thunk is like way at the beginning of program initialization. So first thing I'm going to do is I'm going to open up the source file for this program. I will say things are a little cramped inside of the UI here. That's because I'm running at extremely high DPI so that everything is visible to people out there in the back row. But if you're using a normal display resolution, things are much a bit roomier. So inside of our program, we can see it's quite simple. Basically, in our main function, we just have this vector of values that we're going to aggregate. We have a for loop where we loop over the first 10 letters of the English alphabet. We create a string, we print it out, we add it to the vector, and then so that the program doesn't complete immediately, we sleep for a little while. So the first thing I'm going to do is I'm going to stick a breakpoint here inside the function and hit go. What's now happened is the debugger has replayed execution of the program. So it's replayed all of the instructions that the program actually ran up until the point that this breakpoint is first hit inside of main. And so we can see that if we look inside of the stack window, we can see we're now inside of main, which was called from all the C runtime boilerplate. And in the locals window, we can see that we can actually inspect all the local variables. So I'm going to set a second breakpoint inside of the loop. And so we can see if we run again, we're now inside of the first iteration of the loop. We can see that from the value of C, the current character. And we can see that the values vector contains one element, and it contains the string, the letter A. And if we click go a couple more times, we can see that the program advances forward. If you're familiar with WinDBG and all the commands, since we're using the same debugger engine, most of them still work. So for example, the G command can be used to go forward as well. So now we're in the fourth iteration of the loop. There's two things I want to point out here. So the first is most of the features that work when debugging a live program also work with TTD, right? Breakpoints, stepping and running, inspecting variables in memory. The big exception here is you can't modify the state of the program, right? If you're debugging a live program, you can actually go and we could change the value of one of these strings to be something different. We can't do that because the program's not running anymore. We're just replaying what actually happened in the past. The second thing here is you'll notice that when we're replaying the trace, we don't see the console window. And the reason for that is we don't actually replay any of the side effects of the program. So we don't replay any of the UI. We don't do any file I/O if the program did any file I/O. If your program caused the computer to catch on fire and melt, then replaying the trace won't cause that to happen on whatever computer you're replaying it on. So we've shown that we can replay forwards, but this is a reverse debugging tool. And so we can also replay backwards. So next to the normal flow control buttons here, like go and step into and step over, we also have these reverse flow control buttons. So we can go back or step into backward or step over backward. And there's these nice little tooltips with links to the documentation to help you kind of navigate around these new features. So for example, if I click go back once, we're going to hit our breakpoint again, but we can see that we're actually in the previous iteration of the loop. So we had 4 strings in here before, and now we only have 3. We can see the one with the letter D is gone. And if we hit go back again, now we're in the second iteration of the loop. Similarly, just like we could use the G command to go forward, there's a G- command to go backward. And so here, you can see now we're back in the first iteration of the loop. If you're familiar with WinDBG, you may have used the P and T commands to do single stepping. Those are used to single step forward. There's also P- and T- commands that do reverse stepping, so they do the opposite. So that's the basics of time travel debugging. So we've seen how you can record a trace of a program and how to do basic navigation through the trace in the debugger. But it'd be a lot more interesting to try using TTD to debug a real bug. So for that, I wrote a little program to say hello to all of you. So here it is. It just prints out, hello to everyone at Meeting C++. It's so nice to meet all of you. It really is. And it has this beautiful little UI, and it's, oh, I'm sorry, actually, that's telling me that the program has crashed. That's unfortunate. So that happened to me earlier when I was practicing this, and I managed to record a trace. So let's take a look at that trace and see if we can figure out what went wrong. So I'm going to go back to the File menu in the debugger, and there's this Open Trace File option. And I happen to store my trace right here, so I can just double-click it to open. And when it's open the trace, it would index it if it wasn't already indexed, but I had opened this previously, so it has the index built already. And you can see we're positioned back at the beginning when we started recording this program. Since the program crashed, I'm going to guess that there was an exception, right? It was not necessarily a C++ exception. Perhaps it was a structured exception or something that was raised out of hardware. For more information, I just gave a whole talk at CPPCon on how exceptions work, so you can, on Windows, you can go and watch that talk. But here I want to find out if an exception happened, and if so, when it happened. And to do that, I'm going to use a pretty new feature of WinDBG called the debugger data model. So the debugger data model provides a uniform way of getting information about the thing that you're debugging. You can browse the information using this model page. There's this little tab up here and this option. But we can also use it, browse it using the command window, which I'm going to do here. So first I'm going to use the dx command. So this is to describe a thing. And the information I'm looking at is related to the current process. So I'm going to look at cur process. And I'm just going to see what the options are there. So you can see here, this just has like the name of the process and the process ID. So this was the actual ID of the process when it was running, when we recorded it. And we can see here there's this TTD node. So this will have all the time travel debugging specific information, and I'll expand that. This lifetime is the beginning and end positions of the program. So basically we give each instruction that gets executed gets a unique timestamp. And so this tells you basically the timestamp of the first instruction and the timestamp at the very end of the trace. But the information we're looking for here is an event, an exception event. So we'll just expand that and see what options we have. So in here, we have an array of events, and basically there's going to be one event for every time a module gets loaded or unloaded. So modules are DLLs. I have a whole talk from CPPCon on that as well, if you're interested. There'll be an event for every time a thread gets created or terminated, and then of interest to us, there's an event every time an exception gets raised. So we'll just click that and see what's there, and we're looking for the exception-specific information, so we'll expand that. So what we can see in here is we have the position, which is the timestamp at which the exception occurred. We have the type. This tells us this was a hardware exception, so it was not a C++ exception. It was an exception that was actually raised by the CPU to notify us that something had gone wrong. It has the program counter, which is the address of the instruction that caused the fault. And then it has the exception code, and I happen to know that this code means that it was an access violation. So we tried to read or write or execute some memory that we didn't have access to. We also have this time travel link, and this is next to most of the time you'll see a timestamp. And what this will do is it'll actually teleport us to that time, or cause us to time travel to that position so we can see what was going on. So I'm going to click that. And now if we look at the stack, this is the state of the stack at the time that the exception occurred. But unfortunately, this doesn't tell us a lot about what went wrong, right? Like that, the debugger wasn't able to take that and decode it into an actual function address. So we don't really know where the problem occurred. I also notice something else interesting. If we look at the current state of the program, we can see that the stack pointer and the base pointer point to two completely different locations in memory. And so that should not happen. That's generally a bad thing that happens. And so if we had a crash dump, this is basically all the information that we would have. If we had a full crash dump, we could also go and look at the memory on the stack and try and figure out what went wrong. And then we try and deduce where that data came from and who was responsible for corrupting. This looks like a stack corruption here. And it can be very tedious to debug this sort of thing. But we don't have a crash dump. We have a full trace containing everything that happened. And so we can just replay the trace backwards until we get to the point where the corruption occurred. So the first thing I want to do is replay backward to before the instruction pointer and base pointer registers in the CPU were corrupted. I expect that this happened when the previous function returned, so it's probably just going to be a few steps back. So the first thing I'm going to do is I'm going to switch. You can either do source stepping or assembly stepping in WinDBG, and so assembly stepping, since we want to step individual instructions, we'll do that. And I'm just going to step into back once and see what happens. Well, okay, nothing changed there, so we'll do it one more time. We can now see we've stepped over the return instruction, which has restored the instruction pointer inside of the CPU. So we can see the instruction pointer is now the address of the return instruction inside of main. And we can see the debugger has now been able to decode, okay, I now know where we are inside of the program. But we can't see the rest of the stack, and the reason for that is that the base pointer is still corrupted. So I'm going to guess that the previous thing before that return instruction is that the function would have restored the base pointer based on what was on the stack. So I'm going to step back once more. And indeed, here now we've been able to decode most of the rest of the stack. We can see that the stack pointer and base pointer are both set to pointing to similar locations in memory. But you'll see we still can't see the complete stack, right? Like this still does not look correct. And the reason for that is we've stepped backward to before the CPU state was corrupted, but we still don't know where the actual stack was corrupted. So for example, if we actually take this address and we look at it in the memory window, we can look at what's on the stack. And so we're expecting this to be the return address, the function that we're going to return to, but that looks an awful lot like the end of the string that we printed out. And indeed, it looks like we have, we can observe our stack corruption at this point in time. So what we need to do now is we need to figure out who actually corrupted the stack, right? Who actually wrote that data onto the stack so that we can go and fix the bug. And to do that, I'm going to use a breakpoint. And specifically, I'm going to use a break on access breakpoint, or a data breakpoint. So to do that, there's this BA command for break on access. I'm interested in writes to a 4-byte location, because we're on x86, we have 4-byte pointers. And I'm just going to take the stack pointer and set it on that address. So now if I go back, the program is going, or the debugger is, if I've done it right, it's going to stop at the exact instruction that corrupted the return address on the stack, which is here inside of strcpy. So I don't think the bug is inside of strcpy. I used to work on the C standard library, and that would be very surprising to me if the bug was there. So I'm just going to skip strcpy and go and see where in our function, or in our program, we called it. So here we have this function called getMeetingC++Greeting. And we see that it takes a buffer, and it takes, I guess, the size of that buffer. And then it's got this constant string with the message, and then it just calls strcpy to copy it into that buffer. If we look at the local variables, and we expand them, we can see the entire message, which is the constant message we're copying from. And we can see the buffer, which is not properly null terminated. And the reason for that is that we're actually stopped inside of the strcpy. So this is before we've finished writing into the buffer. The other thing we can see here is that we think the size is hex 64, which is decimal 100. So this means this function thinks there's 100 characters in the buffer. Now, since we know that we've just overrun the buffer, I'm going to guess that it doesn't actually have 100 characters. So maybe our caller passed the wrong data. We can see here it has an array, and no, in fact, it only has 50 characters in it. And it looks like the problem is we've passed the size of the array instead of calling the array.size. And since each wide character is 2 bytes, we've passed a size that's twice too many. So this test program is quite small, and we probably could have debugged it very easily just by looking at the source code, right? Like if I were to expand this, it would all fit on the screen for all of you to look at. But when the same kind of problem occurs in a giant code base, debugging it using traditional debugging tools can be very tedious. And so time travel debugging makes the process much simpler, and it is generally easier. So I'm going to come back to the slides. So just a little recap from those demos. We looked at how to record a process. We looked at how to step forward and backward through a trace once you have it. We looked at how replay is read-only, so you can't modify the state of the program. We looked at the debugger data model, which provides a uniform way of getting information about the thing you're debugging, how to find events easily, how to use memory breakpoints. And this last point is so you can actually set memory breakpoints like using the CPU. So if you're debugging a live program, you can actually set memory breakpoints in the CPU to get that kind of functionality. However, CPUs limit the number that you can have. You can't set an arbitrary number. And so basically, like on x64, you can only set 4 64-byte or 4 64-bit locations that it can monitor. With TTD, there's no limit. You can set, basically, if you wanted to, you could set a breakpoint, a memory breakpoint on the entire address space of the process, and then we would stop many times per instruction because each instruction reads the instruction and whatever its arguments are. But you could actually do that, and there's no limit there. So that's another capability that TTD has. All right. So that was a small program. Maybe we can look at something a little bigger. Additionally, what we've seen so far has been pretty similar to normal debugging, right? We've set some breakpoints, we've replayed the trace, we've inspected variable values and things like that. And yes, we've shown how we can do those things at different points in time, and we've shown how you can navigate forward and backward through time, but conceptually all of this is not too different from how normal debugging works with a live program. Time travel debugging also lets us look at code in a new and interesting way. We can look at execution of a program as a queryable data source. So imagine you had an SQL database table, where each row is a single point in time during the execution of your program. So each row represents the complete state of the program at the point where an instruction was executed. And then we have a set of columns in this table that represents the value of every register and every location in memory at that point in time. And this would be like a humongous table, right? We could not actually store this table for even the most trivial program. But we can imagine having such a table, and we can imagine running queries over this table to help us identify specific patterns of calls to functions or specific memory access patterns and other things like that. And we've enabled this sort of querying using time travel debugging. Another way to look at this is if you've used the sysinternals process monitor. That's another tool which records what a program does, but at a different layer. It records a program's interactions with the operating system, so things like file accesses or registry usage, process creation, etc. And in process monitor, you can filter it to just, say, create file calls from a particular process you're interested in. And we're trying to bring that power to debugging your programs as well. All right. So have you ever had this happen? It's 4 p.m. on a Friday, and you're about to head out the door. You're just getting ready to go home, and you get an urgent email from your boss like this one. So my colleague, Jay Random McHacker, he's working on our new top-secret media player for Windows. And the other Friday, he got this email from his manager. I was trying out your program, and I got this error. And he helpfully included a screenshot, and it's got, you can see the message box that his manager saw. The operation completed successfully. So I'm sure, has anyone seen this kind of error message anywhere? Yeah, right. So it was Friday afternoon. My friend really just wanted to diagnose this as quickly as possible so he could head out for the weekend. And he had a few options. He could ask his manager to send him repro steps, and then he could try to repro the bug himself. But that could take several iterations because, of course, when you ask for repro steps, everybody forgets one, or they forget the most important part, or maybe it wouldn't repro on his machine, and so this could take a while. He could go over and sit with his manager while he watches his manager repro the bug on his machine and then debug it there. But my friend is not a big fan of having people looking over his shoulder while he's debugging. Or maybe he could just ask his manager to record the bug using TTD, share the trace file with him, and that means his manager can repro the bug on his machine, and then my friend can debug it on his own machine without his manager breathing down his neck, and hopefully get it resolved quickly. And my friend's a smart guy, so of course he asked for the TTD trace. He shared that trace with me, and I'm going to show you how he debugged this. So let's open the trace file and take a look. Let's stop debugging this prior one. And we'll just close these source files that we don't need anymore. All right. So again, we've opened this trace file. We're positioned at the beginning of where his manager started recording. I'm going to guess that his manager stopped recording while the message box was still up. He probably killed the program at that point in time. And so let's just see if that was the case. And so we can do that. There's in the debugger, this bang TT command stands for time travel. And you can pass it one of two things. We saw those timestamps earlier that are absolute timestamps that denote individual instructions that we recorded, so you can pass it one of those, or you can pass it a percentage, which is useful for like jumping to a particular, just somewhere during the execution of the program. So for example, if we say bang TT 100, it will jump to the end of the trace, 100% of the way through the trace. And so let's see if our guess was right. And well, no, at first glance, it looks like we're not inside of the get message, or the message box. But this is actually a multi-threaded program, so we can see here there's a lot of different threads running. And we're stopped on this worker thread or some other background thread. So while TTD can record programs that are running multi-threaded, we then basically produce a linear timeline of everything that happened. So this just means that we said this thing happened somewhat later than things on other threads. So I'm going to go check and see if a message box was popped up. I'm going to guess it was on the UI thread, so I'm just going to switch to the UI thread and then look at the stack. And OK, so our guess was actually correct. We are inside of the message box call on the main thread. Now, if that wasn't the case, we could then go and search through the code, set a breakpoint, find it. The point really to show there is it's really easy to just try things out, and if you're wrong, then no problem, you just try something else out. It's not like with a live repro where again, if you try something out and you were wrong, maybe you've got to go back to the beginning and start from scratch. So let's start by looking at who's calling this message box function and see what it's doing. So if we look at the local variables, we can see that it's got this local message buffer, which has the actual message text. And we can see inside of this report last error function, it calls get last error and passes it to format message to get that text. And then it just passes that to the message box function. So a common pattern with Win32 Windows APIs is that the function doesn't actually return what went wrong. It just returns a Boolean, and it'll return true on success or false on failure. And if a function returns failure, it'll set this thread local last error state to be the error code that specifies the specific error that occurred. And then you're responsible for actually calling get last error to get that error code. So a program will typically call a Windows API, check to see if it failed, and if it failed, it'll then get the code and figure out what went wrong. A common programming error, though, is for a program to call a Windows API, but then maybe call a different Windows API before it finally gets around to calling get last error to get the detailed error information. Since that last error is a thread local variable, that second Windows API call that you made, it might overwrite it with some other value. So when the program goes to retrieve it, it'll get the wrong value. And here, when we call get last error, again, the text was the operation completed successfully. So we can guess that the error code was probably 0. So it's likely that we've made this programming mistake here. We can actually check the last error state using, there's a WinDBG command GLE for get last error. And this works with live programs. It also works with time travel debugging. And if we look in here, we can see, indeed, the last error value at this point is 0. So what we want to do is we want to find the original error code. So what was the error code before this got reset to be 0? And to do that, I'm going to write a query to find that error code. So to start with, I want to search for all of the calls to the get last error function. We're going to do that again using the dx command. Here, we're going to start by looking at cur session, which is the top level data model object. We do support tab completion here, so you can kind of browse through things that way if you'd like. The information we're looking for is, again, TTD specific, so we'll look at TTD. And then what we want to do is we want to use this calls function. And this will actually run a query, and we can pass this the names of functions that we're interested in, and it will return all of the times that those functions were called. So here I'm actually interested in two different functions. First, I'm interested in that getLastError function, and I happen to know that that's inside of kernel base. So I will write that. But I'm also interested in knowing where those are relative to the call to message box, right? Because I want to know what was the last call that, to get last error that returned non-zero before we called message box. So message box is in user 32. So we'll ask for both of those. Finally, I want to store this in a variable because I'm going to end up reusing it. So I'm going to hit enter, and this is going to run, and it's going to take a moment. And if we look at the task manager, it's actually going to take about 40 seconds. If we look at the task manager, we can see it's running away, it's doing all this work. And so I'll take this opportunity to say that the debugger here scales very well whatever hardware you're working on. So it works, it works remarkably well on this ultra-portable laptop that I have that is not a developer class machine, and I love it for travel, but I would never want it as my main developer machine. On my 16-core workstation at home, this query will run near instantaneously. So we do scale fairly well to whatever hardware you might be able to throw at the problem. Oh, I can hear the fan running too. It's really working. So it's done, 40 seconds, like I guessed. So what do we have here? Well, this does not look particularly useful. What happened is it returned an array, and so it's just going to say, yes, I have all these objects, and would you like to look at one of them? Another thing we can do is we can view them in grid form. So I'm going to do that by using dx-g, which means show me this in a grid. And I had stored it previously in this calls variable, so I'll just say show me all of the calls in a grid form. All right. Doesn't quite fit because, again, I've got the high DPI for all of your benefit. So let's see what it printed. So each of these call objects, it has an event type. It tells us it is a call. So if we aggregate these with other information, we can determine what each object is. It has information about the thread on which the call was made, because, again, we're recording a multi-threaded program. It has the time start and time end. So these are the timestamp of the first instruction inside of the function when it was executed, and the timestamp of the return instruction. And you can actually see that if you hover over these, it tells you what each of these are. Has the name of the function, which is going to be useful for us, because again, we asked for information about two different functions. It has the address of the function. The return address is the address to which it returned. And then it has the return value, and if we wanted, we could get some limited parameter information. So, by default, these are not in any particular order. We generate them asynchronously, and we just return them as we get them because you don't always need them in order. In this case, I do need them in order, so I'm going to sort them. If you've used C#, you may be familiar with link. So link is basically it's a set of functions and a query language that lets you sort and filter and transform data in a uniform way. And so we actually support that same, a very similar syntax inside of the debugger with many of the same concepts. So what I can do here is on this calls object, I can do an order by. And this is a function that takes a lambda, and this is going to be a C# style lambda. So we're going to say for each call object, which we'll just name x here, I want to sort by the time start. And you can see we can use tab completion there. And so now if we just look at the timestamps of the last few, we can see they're all in ascending order. So great, we've got the results sorted. The next thing I notice is that many of these calls to get last error return 0, so they return no error. So this is common, right? Most of the times that you call a Windows API, like it's going to succeed. If APIs are usually failing, that's kind of maybe indicative that your program is doing something it shouldn't be doing. But we're not interested in any of those calls that return 0 because we want the non-zero error code. So I'm going to filter those out. So what I'm going to do is I'm going to attach to this a where. And so what this will do is this takes a predicate, and the predicate will get applied to each of the objects in the array. And for all of them that return false, it's just going to discard them. So here, I'm interested in all of the calls where either the return value is not 0, or I still want to keep that message box call in there because, again, I want to know how these are located in time relative to that call to message box. So I'm just going to also check for So I'm also going to keep any of these where the message box, it's actually a message box call. Excellent. So now we have all of the calls to get last error that returned, well, I guess I should show it, yes. No more zeros. That was the important point. Finally, this state is thread local, right? So we want to discard any of these calls that might have been made from something other than the UI thread, because again, it's on the UI thread that we're looking at this. So for that, I'm going to attach one more where. And I'm going to only include calls that are made on this current thread, which has thread ID 1634. Cool. So the call that we're interested in is probably one of the last ones, because again, like the program did a lot of things before the message box was popped up. So what I want to do is I want to see how many calls there were in total. And so you can do that by applying a count to this list. This is not going to be an array of things, so we don't use -g. We can see there's hex B86. I actually want that in 10. We'll just switch to base 10 and then rerun it. So there's 2,950 calls. So that's still quite a few calls have failed, though actually the filters that we put in place actually filtered out about 90% of them. So about 90% of the calls returned 0. So that's it's impressive the number of times some of these fundamental things get called in the program. All right, so what I want to do, though, is I want to basically, since we're only interested in the last few, let's just look at the last 50. And so we'll skip the first 2,900. You'll note that this is really fast, like these last few queries we've run. We actually cache all the results internally, so it's not like we have to wait 40 seconds every time we want to do, another one of these filters, which is also important because you don't want to be spending all that time waiting. Anyway, let's scroll up and see if this has the information that we wanted. Okay. So here we can see we have this call. We have our message box W call. Its end position says invalid position. The reason for this is the function has not yet returned. We're still inside of that function when the when the recording was stopped. So basically that just means the function did not return or has not yet returned. But I'm not interested in that call. I'm interested in this previous call because this was the last call to get last error on that thread that returned non-zero. It returned status 122 before we raised the message box. So I'm going to jump to this time by clicking the time travel link. And I'm going to view the stack. And let's see if we can figure out what went wrong. So it looks like we are inside of some Windows OS stuff here. I'm just going to guess that's not where the bug is. Here we have, okay, here's an open file function that looks useful. And so, yeah, well, this looks interesting. My friend says the file name is his manager's important, hilarious jokes text file. My friend tells me that our new media player does not support .txt files. So he was able to tell his manager to, use some other program for that. I hear Windows has maybe a program that can open text files. And then my friend can go home for the weekend and he can, go figure out, what's actually wrong with the message box. Why are we dropping this error code on the floor? But he can do that when he gets back on Monday. So, key takeaways from this. Send me a trace, not a repro. We have teams at Microsoft that, if you say, I have this bug, they'll say, okay, send me a trace file of what happened. We don't want repro steps. We want the actual concrete thing that we can just look at and say, okay, now, we know what went wrong. We know what went wrong in the actual environment where it went wrong. If my friend's manager had sent, repro steps instead, it's likely he would have omitted the exact file name, and so we wouldn't have quite understood, how to repro it, and it would have taken a while. We've seen the power of queries. So these are, still fairly, I know some of them look a little complex, but the link functions that you can apply to these things, like they're applicable to all of the collections inside of the debugger. And again, they're very similar to what's done in C#. So it's, once you learn a few of them, they get very easy to use and firsthand, they just become easy to use, easy to remember how to use. Finally, you got to see the sneak preview of our upcoming media player app. No, I'm just kidding. That's not our upcoming media player. It's one of the Windows 7 SDK samples. And also, those aren't actually my colleagues' names. There's no JRandom McHacker on my team, though I do thank my real colleagues for helping put this demo together. All right. One last demo. So I found that it's actually quite a challenge to put together demos for a talk like this, right? So in a typical talk, you write as small an example as possible to show off exactly what you want to show. And it's often possible to fit the code, that you want to highlight onto a slide or two. Debugging talks are much harder, right? Simplified examples like those first two examples I walked through, they're good for showing off the basics of how the tools work, but they feel rather fake, right? It's easy for you and even for me, when I'm watching talks like this, to look at it and say, well, I could have solved that problem using much more traditional techniques and, much faster than, you did it with time travel debugging, because of course I'm up here explaining everything as I do it. But on the other hand, complex real-world bugs don't usually make for good demos because they're too complex, right? You have to explain way too much and go into too much detail. So for this talk, I spent a lot of time looking for a good example that would be complex enough to be interesting, but not too complex to explain, I hope. 5 years ago, Kate Gregory and I taught an online introduction to C++ class, and at the end of that class, we gave a few examples of software built with C++ as a way to really try and inspire our audience to go and continue to learn more about the language, right? Show the cool things you could build. And I had signed up to put together a demo showing use of the Cinder library, which is it's a nifty open source library for, they call it creative coding. It has a bunch of stuff for writing graphics software, doing audio or video processing, etc. It's pretty cool. Anyway, long story short, I forgot to put together the demo, and that moment is immortalized in a photo on Kate Gregory's blog. But we had other demos, so it was all good. It worked out. But I decided, better late than never, so I put together, a little Cinder demo for this talk. So let's just take a look at that. I have to stop the... I don't know how to escape the PowerPoint. There we go. Okay, so I downloaded it and ran it, and I found just as a starting point, they have this little, that doesn't work, okay. So they've got this little program, they call it a visual dictionary, and it's just got a bunch of things. It's just kind of showing off some of the graphics things you can do. But basically, you can click the letters, and it limits you to only picking letters that could fit that could spell real words. So here we could spell aardvark. Anyway, this would have made a fun little demo for that introduction to C++ talk that we did. But it doesn't make a great talk for this because I'm here to talk about debugging, and that program seems to be working fine. So I decided to look at the source code and see if maybe I could find some subtle, non-obvious bug that I could, show off. While I was looking at the source code, I was shocked because I saw it uses std_list. Now, I've been to a lot of C++ conferences, and if there's a common theme that runs through 90% of the keynotes, it's you don't use std_list, you use std_vector, right? Vector is fast, it's much better. So anyway, this program would surely be much faster if you used std_vector, so I went through and I changed it, just changed all the lists out for vector. Super easy, right? They have a similar interface. You just have to change a few lines of code. So, I built it and ran it, and it's much faster. It's unfortunately, the only thing it does much faster is it crashes. It took an infinitely long time to crash before, and now it crashes in 2 seconds. Okay, well, so I recorded a trace. Let's debug it and see what latent bug I exposed through my little changes here. So we'll stop debugging the prior example. And we'll open our trace file. Excellent. So once again, we're stopped at the beginning of the program. And we want to go find, again, the program crashed, so it's likely that an exception occurred. We want to go find that exception. We could go look in the data model like we did before, but I'm actually just going to click the Go button because I know the debugger is going to stop whenever an exception event occurs. And so if I hit Go, indeed, we hit the access violation. So yes, we know what the problem was, and we're positioned right where it was. So let's look and see what happened here. So this move small function that we're inside of is it's part of memcopy, and I don't think the bug is there. That would be very bad if the bug was in memcopy. So we can look at its caller. Oh, I'm sorry, it's inside of memmove. Well, it would be bad if the bug was there as well. So we're inside of this this move function, and we can see it looks like we're passing this pointer value into memmove. Right, we're pointing this, and I have a little experience. I do not think that is a valid pointer value. That would be disconcerting if it was. But this move function just gets the pointer from its caller, so the bug obviously is not here. We need to find out where that pointer came from. So I'm just going to keep walking up the stack. So its caller is this stdstring assign function, and it also looks like it got it from its caller. So the bug's not there. Go up one more. All right. So here we are. We're inside of the assignment operator of a stdstring. We can see we're actually inside of this call to assign. And we're passing the data from this, basically, the right-hand side of the string. So we're trying to make a copy of the string, and the string we're copying from has, it looks like, incorrect state. And we can verify that by looking at our local variables. I didn't mention this before, but in the debugger, we do pretty print all of the variables and things like that, and we use the same format and debugging information that Visual Studio does. So, all of the STL visualizers still work. If you have your own for your own program, they work in WinDBG as well. But I'll just expand this and see if we can find out where the pointer is coming from. I need to switch back to base 16 because we switched to base 10 before. Okay. So here, I found the pointer. It's in this PTR data member. So we know where that came from. That's good. The second thing that I notice here is the size of the string is 1. So it's 1 character long. And so this buff member, which contains the string n, looks like that is probably the string that we're trying to copy from. So there's a nifty optimization that some string implementations do. Actually, I assume all of them do it. If they don't, then that's problematic. And it's called the small string optimization. I'm sure most people here are familiar with it. But usually a string needs to allocate a buffer on the heap to store its value. With the small string optimization, if the string is short enough, then the string can just kind of cheat and store it inside of itself so that it can avoid that extra heap allocation. In the Visual C++ implementation, this is done via a union, which is this bx thing. So buff and pointer are actually two different interpretations of the same bytes. And we can actually verify that by looking at this character n. And so there's a way in the debugger you can use the question mark to evaluate simple expressions. So we can see that the character n has character code 6e. And if we look at the pointer, we can see that, yes, indeed, the low-order byte is that 6e, and the next one is the null terminator. So our buffer contains those two characters. And when the debugger shows us the value of PTR, which shares the same storage, it just reinterprets that as the pointer type. So right now, it looks like the string has somehow misinterpreted its contents, right? It thinks that it has a pointer to a heap-allocated buffer, but and so it's interpreting this thing as a pointer. But in fact, it has a small string-optimized string. So that's no good. So how does string distinguish between these two representations? It uses its capacity, which is, if we scroll down, it's this myres member here. If the capacity is small enough to fit inside of the small string optimization, then that indicates the small string optimization is being used. If the capacity is larger, then that means that we actually have a pointer to some heap allocated thing. In the Visual C++ implementation, 15 characters is the maximum that can fit in the small string buffer. It's actually 16, but one of those is the null terminator. So 15. This myres, though, has that's a much larger value. I think 0x10f is larger than 15. This is like 271 or something like that. So it's much too large for the small string optimization. So it looks like that's the value that has gotten corrupted somewhere or that has become incorrect. So let's find out who by setting a memory breakpoint on this variable and running backwards. So to do this, the first thing I need to do is get its address. This is a little hard in the locals window. So the other thing I can do is I can use the dx command. And this variable is named write, so you can actually use dx to inspect variables, just like you can inspect all the other objects. And what I'm going to do is I'm just going to browse until I find this myres thing inside of here. And so you can just click these links, and it makes it very handy, so you don't have to remember any arcane commands. I don't remember what half of the commands are in here. I just click things until I find what I'm looking for. And, here it is. So we can see I've got myres here, so I'm just going to take that previous command that I ran and look at it, and so we can see it's going to print out that its value is 10f. I'm not interested in its value, though. I'm interested in its address, and so you can actually get that in C++. You just apply the ampersand to something to get its address. You can do that in the debugger as well. And so we can see here, this is the address of that. So what I'm going to do is I want to know who wrote to it, so I'm going to set a data breakpoint. So I'm going to use BA for that. We're interested in writes. This is a 64-bit trace, not a 32-bit, so this is a size T thing. It'll be 8 bytes in size, and then we're just interested in that address. So now that we've set the breakpoint, I can just hit go back, and now we're at the point where the data corruption occurred, where we corrupted that. So if we look at the code, it looks like we're actually setting a Boolean, which is not. That Boolean cannot be inside of that string, I don't think. So I'm interested, what does the program think the address of that Boolean is? Okay. So it thinks the Boolean is at this 364C0311, and we think that our capacity is at 364C0310. So my guess at this point is that we have a use after free bug, that we had a word node allocated at one location and stored its address. Later we freed that, and then that memory was later reused for something else. So at this point we could use normal debugging techniques, but I want to show off one more really cool querying capability that we have. So we saw before that you can query for calls. You can also query for all of the accesses to a particular byte of memory. So what I'm going to do is I want to see all of the people who wrote, all the instructions that wrote to this location in memory. And so to do that, I'm going to use dx again. It's going to give us a list of things. So I'm going to use the grid form. We're going to look at the current session again and ttd. And instead of doing calls, we're going to do a memory query. This query takes 3 parameters, and this is all documented online. The first parameter is the first address of the range that you want to look at. The second parameter is the last address, so I'm just going to add 8 to that because we're interested in that 8-byte region. And then the third parameter is the access, the kinds of accesses you're interested in. So here I'm interested in a W. Now when I hit enter, this query is actually going to be quite fast because there's not too many writes, so it's very easy for it to find all the information. These are all of the writes that happened to that 8-byte location in memory in the entire duration of the program. I'm running a little short on time, so I wanted to highlight, I guess, just the important things here. The first is this second to last write is very interesting because we're writing a 0f, so that's the value 15. Now 15 is the value that we expect this location in memory to have, right? Because that's the capacity for the small string optimized thing. And so if we time travel to the location of that write, we can see that indeed, I hope, we are inside of the string constructor, which is where we expected it to be. Then if we were to go to the location where this next write occurred, we would see that we're back inside of that place where we were writing the Boolean and actually corrupting the value. to look at the, I guess, the fields here. These last three are the most important. So one is the address. So this is the address it's being written to. And this is the size, so it's the number of bytes that are being written by that instruction. And then the value, which is the actual contents of the bytes. So if we look down here, we can see that when we wrote the 0xf, the value 15, it was an 8-byte write. So we were writing to the entire 8-byte location at that address. However, when the code actually corrupted it because of the use after free, it did not write to the first byte. It wrote to the second byte, right? And it was only a single byte write. So that was the write of that Boolean. The other thing I wanted to show in here is you can see interesting patterns of writes. So for example, here we can see a series of 8 writes of the byte CD. And we can see that they're all 1-byte writes, and they're writing to consecutive addresses. So here we're at address 0310, 0311, 12, 13, etc. These, if we were to look at the call stack, we would see this is actually inside of the debug malloc implementation. So in the Visual C++ debug runtime library, it actually fills in new allocations with this special pattern CD to help you find uses of uninitialized memory. And so that's actually what we're seeing here. So you can actually see these kinds of access patterns inside of this using these queries. So the piece of debugging that I was going to walk through in a bit more detail, if I hadn't run out of time, was here we can see an allocation, and then we're using that region of memory. Later, we're seeing a deallocation. The free implementation fills in with this DD pattern to let you know when you're using memory after you've freed it. And then later, we can see we've reallocated in that same location. So we can see that we are actually getting 2 allocations. And if we look at the call stacks at those locations, we would see that it's all happening basically inside of a loop. So yes, unfortunately, I've run out of time. I guess the important thing is this was all because we were calling pushback in a loop and taking addresses of the objects that we were putting into the list. So that worked when you had a std list because objects don't get moved around in memory. But when I switched it to a vector, it didn't work anymore because when you push back, it might have to reallocate the storage for the vector. So the bug was actually I was disappointed to learn it was my fault. But that's actually a common experience for me. So it's All right, so being out of time, wrapping up most important things, time travel debugging is awesome. You can download it today. It's available in the Microsoft Store. It is free, so there's, you just go download it and try it out. The worst that happens is you hate it and you delete it and you send me hate mail, and I'm okay. I am thick-skinned. I can live with that. And the documentation is available at akams/tdd. So with that, I'm happy to take questions if people want to come up. I'm sorry that there's not time here at the end of the talk. But anyway, I'm happy to chat about this for the rest of the day, and certainly, right now, if people want to come up. So with that, thank you.